This is Professor Pelton. This is part 2 of chapter 7, section 2. So you can, within the unit circle, make special right triangles. So, for example, any anything that divides the 360 degrees all the way around perfectly will make a special right triangle, right? So if we go all the way around, that's 360. So a 30, 60, 90 triangle, a 45, 45, 90 triangle, a 60, 30, 90, which is the same thing as a 30, 60, 90, right? You can also divide 360 by 120, so on and so forth. So any angle that divides 360 perfectly will make a special triangle. The most common special right triangles that are used are the 30, 60, 90, and the 45, 45, 90. And that's how they arrive at the measures that are in the unit circle. So if you wonder how do they get those coordinates, they're using these special triangles. So what's said about the 30, 60, 90 triangle is the 30-degree side is half the hypotenuse, and the 60-degree side is root 3 longer than the 30-degree side. So how do they arrive at that conclusion? Why is that always true, regardless of how big the triangle is? Well, if you take two of them and put them together, you're going to get a 60, 60, 60 triangle. So an equilateral triangle, right? So essentially you get 2t, 2t, and then 2t, right? So the only question is, what is the height? Well, if I do Pythagorean theorem, right, I'm going to get t squared uh, plus um, h squared equals 2t squared. So essentially I'm only taking one triangle, right? Okay, so I get t squared plus h squared equals 4t squared. So if I subtract 1, I get h squared equals 3t squared, or h equals the square root of 3t squared. So h equals root 3 times t. It's really plus or minus, but we don't need the negative one in this case. And that's essentially why the 60-degree side is root 3 longer than the 30-degree side. Okay, so we always know that as a relative case. Okay, and that is how they arrive at all of the 30 and 60-degree triangles all the way around the unit circle. Right, so you get the 30-degree triangle here, and you get the two side lengths, right? So we get the cosine and the sine, right? So this is cosine and this is sine for that coordinate that's on the unit circle, right? And it repeats itself all the way around the unit circle, right? Because each of these, so 210, is obviously another 30-degree triangle in this quadrant actually. Okay, so the other ones in this unit circle are the 45, 45, 90. How do they arrive at the fact that the hypotenuse is root 2 larger than the two other sides? Well, we know for a fact it's 45, 45. It must be isosceles, right? So therefore, the hypotenuse squared must equal a leg squared plus a leg squared, right? So h squared equals 2t squared. So h equals the square root of 2t squared. So h equals root 2 times t. Again, plus or minus, we don't need the negative one in this case. So we've just proven to ourselves the hypotenuse is root 2 larger. And conversely, if you go the other way, the legs must be root 2 smaller, okay? So we can use this information to relatively solve a triangle quickly without doing any calculations. So if we have a 30, 60-degree triangle, and the shortest side is 5 centimeters, that must be the 30-degree side. So using the 30, 60, 90 rules, that means the hypotenuse must be 10 centimeters because by rule, it's twice as long. And the 60-degree side must be 5 root 3 because it's root 3 longer than the 30-degree side by rule. Okay? All right, pause the video, try the student problem for yourself. Okay, so let's draw a pseudo diagram for the given situation. We'll ladder up the wall. So a pseudo diagram is just a one that has the shapes, but none of the actual pictorial or colors, anything like that. So we're going to say this is 60 and this is 30, not to relative size, of course. I could probably draw a better triangle than that, to be honest. That wasn't very good, right? So that's 60, and this is 30. The 60 doesn't always have to be the base angle. It could be flipped, obviously. Okay, so we're saying that the ladder determine the length. All right, so the ladder reaches 4 feet up the wall. Okay, so that's 4 feet because that is the wall. So this is shorter down here. So this is 4 divided by root 3 feet because the other 30-degree side is shorter, right? Determine the distance from the ladders from the wall. That's what we just found. Determine the length of the ladder. So that's twice as long. So that's 8 over root 3 feet because that's twice as long as the 30-degree side. Okay. All right. Let's try the next page. All right. So let's do a pseudo diagram for the 45, 45, 90. It's for the tent. Sorry, for the tent. Okay. So we do the tent here. There's the string or the rope, and we have two 45-degree sides, 45 or 45-degree angles rather, and my terrible 90-degree angle, and my terrible art skills. Probably should go up more like that, huh? Oof, not sure that's any better, to be honest. That's why I teach math, not art. Okay. All right, that's somewhat presentable. Okay, what did I have here? 10-foot rope. All right, that's 10 feet. Okay, so we know that the legs must be smaller because the hypotenuse, which is across the biggest angle, is always the biggest side. So these are root 2 smaller by rule. Okay, so a lot of students get the root 2s and the root 3 mixed up. Remember it this way. A 30, 60, 90 triangle has 3 different angles. That's the one with root 3. A 45, 45, 90 has 2 of the same angle. That's where you use a root 2. Okay, all right, pause the video. Try the student problems for yourself. Okay, so if I have 45, 45, 90, so we'll draw that. That one's not bad, actually. So we have 45, 45. Okay. The hypotenuse is 120 meters. Meters, not degrees. What am I doing? Sorry. So the legs must be smaller by a factor of root 2. So these are 120 divided by root 2 meters and 120 divided by root 2 meters. Okay. Given the non-hypotenuse side of 25 inches. Okay, so draw this again. So this is 25 inches, right? That's 45 degrees. That's 45 degrees. That means the other one also must be 25 inches, right? And this means the hypotenuse must be longer, so 25 root 2 inches. Okay? All right. So relating that to sine, cosine, and tangent in the unit circle, because we talked about the unit circle and how when we did the unit circle, it gave us a coordinate on the circle, which gave us the cosine and the sine value, right? So for 30 degrees, we're saying that cosine is root 3 over 2, and the ratio for sine is 1 over 2, or 1/2, right? So why is that? And at 60 degrees, right, we're saying that the cosine is 1/2 and the sine is root 3 over 2. And at 45, we're saying they're both root 2 over 2, right? Obviously, there's other angles in between here. But they don't work out quite as nice unless they're divisible by 300 into 360. Okay, so using our special right triangle rules, why do these in fact work? So using the diagram to the right, we know that the sine is the opposite over the hypotenuse. So regardless of what t is, I get 1 over root 2. Okay, so cosine is adjacent over hypotenuse, and then you're asking yourself, well, wait a minute, which 45 are you using? Well, it won't matter because in both cases, whether you use this 45 and this 45, the adjacent and the hypotenuse are both t. And then adjacent over hypotenuse are both t in this case, so I get 1 over 1. So if I reciprocate these, I get 1 over 1, root 2 over 1, and root 2 over 1. And what you might see in the diagram I just showed you from when I pulled off Google real quick is it didn't have 1 over root 2 because they'll rationalize the fraction, so they'll multiply by root 2 over root 2 and get root 2 over root 4, or in fact root 2 over 2. So root 2 over 2 is what's called the rationalized form because it doesn't have a radical in the bottom. That's what the diagrams will show online. They will not show the unrationalized form. You only need the rationalized form if you're going to add fractions. Just makes it easier. Okay, so if I do the 30 degrees for the next diagram, right? So I'm doing this 30 degrees here. The opposite of that is t. So the opposite over the hypotenuse gives me 1/2. Okay, so that's why we saw in the diagram that sine of 30 degrees is 1/2. So the adjacent is t root 3 over the hypotenuse, which is 2t. So I get root 3 over 2. And then finally, the tangent is the opposite over the adjacent. So I have 1 over root 3. So if I reciprocate these, I get 2 over 1, or simply 2, 2 over root 3, and root 3 over 1. And again, the books will rationalize those. I'm not going to here. It's not necessary. Okay, so if I do 60 degrees, the opposite is t root 3 over the hypotenuse, which is 2t. So I get root 3 over 2. The adjacent would be t, and the hypotenuse is 2t. So I get 1/2. So I get 2 over root 3. I get 2 over 1. And lastly, 60 degrees, opposite over adjacent, t root 3 over t, or simply root 3 over 1, or 1 over root 3. So you can see in comparison 30 to 60, or just flipping the answers, which will play into our next part of the lesson. That is the end of part 2.